So this is the next practice paper for unified chemistry. So the first question looks at oxidation numbers and wants to tell the oxidation number of nitrogen. So of course oxygen takes priority over nitrogen, so oxygen is going to be -2. So that means for this first molecule, oxygen here comes to -8. So the two nitrogens must come to +8, so each nitrogen is +4. For this one, the three oxygens come to -6, and therefore nitrogen must be +5 to give an overall charge of -1. And here the four hydrogens come to +4, and therefore nitrogen must be -3 to give you that overall charge of ammonium for +1. So the next one is what mass of KMnO4 is needed to prepare 250 centimeters cubed of solution with a concentration of 0.2 moles of KMnO4. So the first thing I do is find the number of moles of KMnO4 in 0.2 moles per decimeter cubed when I've got 250 centimeters cubed. So in 250 centimeters cubed, I will have 0.05 moles of KMnO4. And then to find the mass, I times it by the molar mass of KMnO4 to give me 7.9 grams. So what are the units of a rate constant for a reaction with an overall order of 3? So these are the units for rate, and concentration is here, and that is going to be cubed because it's overall order 3. So this is going to cancel with that to be squared, and therefore the units that I end up with are going to be moles to the -2, decimeters to the power of 6, seconds to the -1. How many molecules are there in 38.25 grams of tartaric acid? So first you need to find your molar mass of the acid, which is 150. So the number of moles is 38.25 divided by 150, which gives you 0.255 moles. And for the number of molecules, you times it by Avogadro's number, which you can find in your data sheet, to give you 1.54 times 10 to the 23. And notice you need that to be 3 significant figures there because Avogadro's constant is given you to 3 sig fig. Okay, so for this one, we're looking at the elements in periods 3 to 4, and we're looking at their melting points. So we need to, first of all, focus on period 3. So let's look at the trend. Well, as you know, you need to talk about silicon. Silicon has a very high melting point, and that's because you've got a giant covalent structure, and when you melt silicon, you are breaking very strong covalent bonds between the atoms. Okay. For phosphorus, sulfur and chlorine, you have got simple molecular structure. The forces between the molecules are London forces, and the reason they're so low is because London forces are weak. If you look at the comparison of these, you see that sulfur has the highest melting point, and that's because sulfur exists as S8 molecules, which has more electrons than Cl2 and also P4. So that's ordered because of the number of electrons. Sulfur has the most electrons in each molecule, followed by phosphorus, and then chlorine, as only being Cl2, has the fewest number of electrons. Okay, let's have a look now at period 4. So period 4 shows a similar trend for germanium, silicon and bromine. However, arsenic has a much higher melting point, and therefore that suggests that arsenic is actually a giant covalent structure rather than simple molecular when you compare these two here. And that's why arsenic has a much higher melting point than phosphorus. So we then have a titration calculation here. So first of all, we have to work out the titers, and remember, for your titers you must take that to 2 decimal place, with your final decimal place being either a 0 or a 5. You do your average, and your average is going to be between these two here because they are within 0.1 of each other to give you 21.75 centimeters cubed. For your uncertainty, you need to times this by 2 because you read your burette twice, the final and initial reading. For titration 3, your titer was 21.70, so it's 2 times 0.05 over 21.7 times by 100 to give you 0.46%. So for the next question, we're going to have to do work out the molar mass. So we're going to work out first of all the moles of S2O32 minus and relate it to copper. So before we turn the page, what you need to notice is 2 Cu2 plus gives you 1 I2, and 1 I2 reacts with 2 S2O32 minus. So the ratio to copper to thiosulfate is 1 to 1. So it says in step 2, why is an excess of Ki added? You add an excess to make sure that all the I2 is formed as needed. As the endpoint of the titration is approached, we add starch to determine more accurately the endpoint, and that gives you a blue to colourless endpoint. And then finally, we're going to determine the formula of compound A. So first of all, you work out the moles of thiosulfate, and as I said previously, that will be the same number of moles of copper 2 plus, but that's in 25 centimeters cubed, and the original mass was dissolved in 250, so I need to times that by 10 to scale that up. And then you need to find your mass of A. The mass of A is 5.6 grams. And therefore your molar mass of A is 5.6 divided by your number of moles, which you worked out up here, which is 2.61 times 10 to the minus 2 rather, to give you your molar mass of being equal to 214.6. So you take your 214.6 and you take away from that CuSO4. That will give you the mass of water. You divide that by 18, which is your molar mass of water, to tell you the number of moles of water molecules, and your answer is 3. So your formula is CuSO4.3H2O. Right, so now looking at a redox reaction that takes place with copper being heated with sulfuric acid. So once, first of all, the electronic configuration for a copper atom. Notice for a copper atom, you have this unusual electronic configuration where you have 4s1 3d10. What you would expect that to be, of course, is 4s2 3d9, but it's not. So you need to remember copper and chromium are both a little bit odd there. Now it wants me to suggest an identity of the colourless gas that I produce. So it's told me that 95 centimeters cubed of the gas has a mass of 254 meg. So I can find the number of moles of gas by taking 95 and dividing it by 24,000, because 1 mole of any gas occupies 24,000 centimeters cubed, to give me this number. Then to find the molar mass is just the mass in grams divided by the molar mass to give 64.1. And therefore it's kind of looking at a likely suspect really for that. And you've got sulfur, you've got oxygen knocking around, so you're looking at that being sulfur dioxide. Then for the equation, so your blue solution, of course, is going to be copper sulfate. Your gas you worked out. If you have a look, you've got some hydrogens knocking around, which are likely to form water, and you balance it up and you get that equation there. Okay, so this is quite a nice question really. Experiment 1. Student adds iron filings to dilute acid, form a green solution and bubbles. So that is the two electrode potentials that I put in blue there in the equation I put in blue. your gas is obviously going to be hydrogen and your green solution Fe2 plus. For the next equation, that's going to be the one in red, because it says I bubble solution air through that solution, which we know is Fe2 plus. Air, of course, is going to be the oxygen. Combine those equations. So I need to times this equation here, of course, by 4, because the oxygen equation has got 4 electrons in. And then finally for experiment 2, they're going to be the two equations in green. It says I start off with chromium 3 plus, which is this equation here, and I react it with hydrogen peroxide, which of course is that. Combine them, but you need to times this equation by 3 to make sure you've got 6 electrons. And if you combine them, you will notice that the waters, this 6 H2O will cancel out with the 7 H2O here to just leave you a 1 H2O. The 6H plus here cancel with the 14H plus to leave you with 8H plus. Okay, so moving on to question 3 then. We have looked at the pH as we've added sodium hydroxide to some ethanoic acid. So how could I measure this pH continuously? Well, I'd use a pH probe on a data logger. Now I need to determine the concentration of ethanoic acid. So if you have a look, that I've reached my endpoint, the vertical section of that graph, at 22 centimeters cubed of sodium hydroxide. So I can find my moles of sodium hydroxide. That's going to be the same as my number of moles of ethanoic acid, because ethanoic acid is monobasic. But that was in 25 centimeters cubed. So it's that number of moles divided by 25 times by 1000 to give me 0.110 moles per decimeter cubed. So if I have a look, which indicator would I use? Well, I'd use brilliant yellow to do this one, because the vertical section on that pH graph matches the pH range of the indicator. Okay, so it's given me the structure now of methyl red, and it wants me to draw the conjugate base. So if you have a look, where's my acid group? Well, I've got a carboxylic acid there, so the conjugate base, I'm going to lose it to form this molecule here. And why, and explain in terms of equilibrium the colours of methyl red at low pH, high pH, and the endpoint. Okay, so obviously at low pH, I've got lots of H plus present. The H plus will react with the A minus to form HA. If it's at high pH, I've got OH minus, so that will react with HA and the equilibrium will shift to A minus. And at equilibrium, the concentration of HA and at the endpoint rather, the concentration of HA and A minus is the same, and therefore it's a combination of red and yellow, which will give me an orange colour. So it tells me now that aspirin is a weak acid with a pK value of 3.4 and a solubility of 1 times 10 to the minus 2 grams per centimetre cubed. It wants me to calculate the pH of a saturated solution of aspirin in water at body temperature. So first of all, I can find the moles of aspirin that I have. So I've got 1 times 10 to the minus 2 grams of aspirin, so I divide that by 180, which is the molar mass of aspirin, but that's in every centimetre cubed, and as we know, concentration is in moles per decimetre cubed, which is 1000 centimetres cubed, so I need to times this number by 1000 to find the number of moles of aspirin I can dissolve in 1000 centimetres cubed. I can then find my Ka. Ka is 10 to the minus pKa, which gives me this value here. And then my concentration of H plus is going to be the square root of my concentration times my Ka. And that gives me 4.70 times 10 to the minus 3. And then your pH is minus log to that value, and that gives me a pH of 2.33. Soluble aspirin is usually sold as a sodium or calcium salt. Why a salt of aspirin more soluble than aspirin in water is because, of course, salts are ionic, and ionic salts will be attracted to the polar water molecules. In our stomach, that contains hydrochloric acid. Well, if it contains hydrochloric acid, if I swallow soluble aspirin, the carboxylate group will react with H plus to form the carboxylic acid again, and the aspirin will precipitate out in my tummy. So I put down here the how to prepare 8.1 gram of pure aspirin. So first of all, I find the moles of aspirin that I require. I then need to times that by 100 over 90 to find the moles of 2-hydroxybenzoic acid I need, which is 0.05 moles, and times that by my molar mass of 2-hydroxybenzoic acid, which is 138, to find that I need to start with 6.90 grams of 2-hydroxybenzoic acid to end up with 8.1 grams of aspirin. Okay. Now, how do I get a pure sample of aspirin? Well, I'm going to cool the reaction mixture down and filter the product off, and then I would recrystallize my my impure aspirin. So I dissolve the impure solid in a minimum amount of water, hot water. I then cool it down and filter the solid and wash with cold water and dry. Okay, so I've now got the RF values of 2-hydroxybenzoic acid and aspirin, and I've got to draw on the chromatogram what the student would get. The student concludes that impure aspirin is contaminated with a small amount of unreactive 2-hydroxybenzoic acid, so I've got to draw spots. So the key thing is you'll notice that this spot here is smaller than 2-hydroxybenzoic acid and smaller than this one here, because it says that it only contains a small amount of 2-hydroxybenzoic acid. So this spot here is going to be bigger because it's mainly aspirin, but I've got a small amount of 2-hydroxybenzoic acid. What would the melting point of impure aspirin be? Well, pure aspirin 138 to 140, so it's going to be lower than that if it's impure, so 130 to 140, and is going to have a range of more than 2 degrees C. So question 4 now. You wouldn't have met ethers before probably, but here are a couple of ethers here. And it wants me to draw the skeletal formula of the ether 2-ethoxy-3-methyl-butane. So if you have a look at this one here, this is 2-ethoxy-propane. So you've got your 2-ethoxy there, which I put there, and then you've got to put 3-methyl-butane there. So this here is your butane, and then this will be your 3-methyl group. Okay. So ethers can be prepared by nucleophilic substitution of haloalkanes with alkoxide ions. How can I prepare them from sodium? Well, you won't have seen this reaction before, but you're going to take sodium with your methanol, and it tells me a gas is produced. That gas is going to be hydrogen, of course, to give you your alkoxide or methoxide ions and your sodium ions here. So how is that mechanism likely to work? Well, of course, you've got your, this is going to be nucleophilic substitution, which you've seen before. In comes your alkoxide ion. That's going to attack your delta plus carbon, and your delta minus bromine is going to leave. Okay, what type of bond fission is this? Well, it's going to be heterolytic because the methoxide ion donates a pair of electrons. Okay, so final page now. So we've got to predict the proton NMR of 2-ethoxy-propane, which I've just drawn here. So we're going to see 2 peaks for OCH that's going to be here. So that's going to have a relative peak area of 2, and it's going to come between 3 and 4.3, and it's going to be a quartet because it's got 3 protons on here which will be splitting it. You're also going to see a peak for OCH here, which will have a relative peak area of 1, and that will be a heptet because you've got 6 hydrogens to split it. The 6 will be there and there. And then finally you're going to see a peak of intensity 6 for those between 0.5 and 1.9, and that's going to be a doublet. So that'll be this peak here, and then you'll see this peak here, a relative peak area of 3. That will be a triplet because you've got 2 neighbours there. And then finally, we're going to see how can I complete this mechanism here. So I've got to get to this intermediate, and you notice it's lost a hydrogen. So it's lost H plus, hasn't it, to give me C minus. So this methoxide ion comes in and takes the H plus away. And the electrons from my CH bond here go to the carbon. And then for the intermediate, I react it with my halogenoalkane to form a nucleophilic substitution reaction to add the ethyl group there. And obviously you'll make Br minus. And explain how those methoxide ions have acted as a base is because they have accepted a proton.